Welcome back to the Deep Dive. Okay, today we are really jumping into the deep end. We're tackling one of the biggest mysteries in physics, something that genuinely makes you question, well, everything you thought was solid and real.
We're talking about the double-slit experiment. And maybe the best way to start is with Niels Bohr, who famously said, if quantum mechanics hasn't profoundly shocked you, you haven't understood it yet.
That pretty much sums it up. So our mission today is to follow this shockwave, right? Starting way back, simpler times, and see how this one experiment spirals into questioning reality itself.
Exactly. We'll track it from the 19th century, see how it shattered classical ideas, and then explore the really wild stuff, consciousness, time, maybe even the idea that this universe isn't, the base reality, simulation, something else.
Let's ground ourselves first. Part 1, the history. We go back to 1801, Thomas Young. No quantum weirdness yet, just light.
Right. At the time, the big debate was, is light a stream of tiny particles, like Newton thought? Or is it a wave, like sound traveling through air or ripples on water?
So Young set up this pretty ingenious experiment. Shine light at a barrier, but the barrier has two very, very narrow slits in it. Then look at a screen behind it.
And if light is just particles, think tiny bullets, what should you see?
Easy. Two bright lines on the screen, basically shadows of the slits, one line behind each slit.
That's the common sense prediction. But it's not what Young saw. Not at all.
He saw stripes, alternating bright and dark bands across the screen.
Yep, an interference pattern. And that pattern is the absolute smoking gun for wave behavior.
Okay, explain that. Why do waves make stripes?
Think of water waves. If you drop two pebbles in a pond, the ripples spread out. Where two wave crests meet, they add up a bigger wave, brighter light in this case.
Okay, makes sense. Constructive interference.
Exactly. But where a crest from one slit meets a trough from the other slit,
they cancel out.
They cancel out completely. Destructive interference. That gives you the dark bands, places where the light waves have literally nullified each other.
Well, wait, nullified? Does the energy just disappear? Vanish into nothing?
Good question. No, it doesn't disappear. Physics doesn't like energy just vanishing. It's conserved.
So where does it go?
It gets redistributed. The energy that would have landed in those dark spots effectively gets pushed into the bright spots, making them brighter. Mm-hmm. It's all still there, just rearranged by the wave interference.
Okay. So Young's experiment pretty much settled it for a while. Light is a wave. End of story.
For about 100 years, yeah. That was the classical picture. Light's a wave. Done. But then, the 20th century happened.
And things got weird. Part 2, the quantum shock. Physicists decided, hey, let's try this again, but not with light waves. Let's use electrons.
Electrons, which everyone knew were particles. Mm-hmm. Tiny, fundamental bits of matter. Little bullets.
So fire electrons at the double slits, you'd expect?
Two clumps of electrons hitting the screen right behind the slits, just like the marbles.
Oh, no.
But no. Unbelievably, they got the same interference pattern. The electrons, these definite particles, were behaving like waves, spreading out, interfering with each other or something.
Okay, that's deeply strange.
But it gets even stranger, doesn't it, when they slow it down?
Oh, yeah. This is where your brain starts to melt. They adjusted the equipment to fire electrons one at a time. So, one electron leaves the gun, flies towards the slits, hits the detector screen.
As a single dot. A particle impact, like it should.
Exactly, one dot. Then another electron fires, another single dot somewhere else, then another. Each one lands as a localized particle.
Okay, so maybe they are particles after all.
But here's the kicker. Let the experiment run. Let thousands, millions of these individual dots build up over time. And what pattern emerges from all those single particle-like impacts?
Don't tell me the interference pattern, the stripe.
The strikes, the wave pattern reemerges statistically from countless individual particle hits.
How is that even possible? It's like each electron, traveling alone, somehow knows about both slits. It has to interfere with itself.
That's the mind-bending conclusion. It acts as if it goes through both slits simultaneously. This forced physicists to abandon the idea of a definite path. So this is where probability comes in. We can't say where it is, only where it might be.
Precisely. Enter the wave function, symbolized by the Greek letter psi. It's not a physical wave like water. Think of it as a possibility wave.
Possibility wave.
Yeah, it's a mathematical description that contains all the potential states, all the possible positions the electron could be in before we measure it.
So for that single electron, the wave function as psi is spread out goes through both slits,
And that mathematical wave, that psi interferes with itself.
creating the probability pattern for where the electron is likely to land.
Exactly. The interference happens in the realm of potentiality, described by Baz. The electron itself only becomes real at a single point when it hits the screen.
And that act of hitting the screen, that's a measurement.
That's one type of measurement, yes. And that measurement is what seems to collapse the wave function, forcing possibility into actuality.
This completely destroyed the old clockwork universe idea, didn't it? Determinism is out the window.
Utterly shattered. At its heart, quantum mechanics is probabilistic, not deterministic. We can calculate odds, amazing odds, but we can't predict the outcome for any single event with certainty. Chance is fundamental.
Okay, let's move to part 3, the observer paradox. This feels like the absolute core of the mystery.
It really is. So the weirdness happens because the electron acts like it goes through both slits. The obvious question is, what if we just look?
Yeah, what if we put a detector, like a tiny sensor, right at one of the slits, or both, to see which path the electron actually takes?
You'd think that would just tell us the path, right? We'd see, okay, this electron went through the left slit, that one went through the right.
But physics isn't that kind.
Not at all.
Yeah.
The instant you place detectors at the slits, the instant you gain that which path information,
The interference pattern
vanishes. Gone. The electrons immediately stop acting like waves and start behaving like well-behaved particles again and just pile up in two distinct clumps behind each slit. No stripes.
So the very act of observing which path it took forces it to take only one path. It kills the wave behavior.
That's what happens. This is the famous collapse of the wave function. The measurement forces the particle out of its state of superposition, being in multiple states at once, and into a single definite state.
But what is a measurement? Does it have to be a conscious observer? Or is just the physical interaction with the detector enough?
Ah, the billion-dollar question. That's been debated for a century. This sort of standard view, the Copenhagen interpretation from Bohr and Heisenberg, basically says the physical interaction is sufficient. Don't ask about consciousness, it's just physics.
But feels like there should be more to it.
It certainly feels that way, and this ties directly into Heisenberg's uncertainty principle.
Right, the equation delta x, delta p, gig bar 2, looks scary. What's it mean here?
It's not about faulty equipment. It's a fundamental limit baked into nature. You cannot know both the exact position, and delta the day, and the exact momentum, delta p, of a particle simultaneously. There's a trade-off.
So in the double slit,
when we set up the detectors to find the position which slit, delta U becomes small, very certain. We inherently disturb its momentum. Delta P becomes large, very uncertain. And momentum is linked to its wave-like nature.
So knowing the path position destroys the waviness, momentum info. You lose the interference.
Exactly. Nature forces a choice. You can observe it as a particle with a known path, or let it be a wave with an unknown path, but you can't have both at the same time.
Okay, and just when you think it can't get weirder, there's entanglement.
Right. Spooky action at a distance, as Einstein famously called it, because he really didn't like it.
Two particles linked no matter how far apart, measure one and you instantly know something about the other one, faster than light.
Instantaneously. And this isn't just theory. It brings us to John Bell and his work in the 60s.
Bell's inequalities.
Yes. Bell figured out a mathematical way to test if this spooky connection was real, or if there was some hidden information, local hidden variables carried by the particles from the start that determine their properties.
Kind of like they secretly agreed beforehand how they'd behave when measured?
Sort of, yeah. If those hidden variables existed, there'd be a limit to how correlated the measurements on the two distant particles could be. Bell calculated that limit.
And experiments were done.
Many times, with increasing precision. And the results consistently violate Bell's inequality. The correlations are stronger than any local hidden variable theory could allow.
So, no hidden instructions. The connection is real. The universe is non-local.
That's the staggering conclusion. Measuring one particle genuinely, instantly influences the state of the other, regardless of distance. Locality, the idea that things can only be affected by their immediate surroundings, seems to break down at the quantum level.
Wow, okay. Let's push this even further. Part 4, time warps and digital ideas.
Yeah, let's talk about modern twists. Quantum eraser and delayed choice experiments. These are even more mind-bending.
Delayed choice, what does that mean?
It means you can decide whether to measure the witch path information after the particle has already gone through the slits and, theoretically, already decided whether to act as a wave or a particle.
Wait, how? The particle's already hit the screen, hasn't it?
In some setups, yes, but the information about its path can be routed through a longer path, involving entangled partner particles. The experimenter can choose, later, whether to preserve that path information or erase it quantum mechanically.
And the choice affects the past.
It appears to. If the experimenter chooses to erase the path information later on, the pattern that built up earlier on the main screen shows interference stripes. If they choose to keep the path information, the earlier pattern shows no interference, just the two particle clumps.
So the particle's past behavior wave or particle isn't fixed until a future measurement choice is made. Reality is deferred.
That's how it seems. Time itself gets weird. This is where analogies to the digital world, like simulation theory, start looking, well, strangely relevant. Scott Adams often brings this up.
How does that connect the deferred reality thing?
Think about efficiency. If you're running a massive simulation like a universe, why render every single detail all the time, especially if no one's looking?
You wouldn't. It'd be a huge waste of processing power.
Exactly. So maybe the universe operates on a need-to-know basis. It keeps things in a state of potentiality, the wave function signacular, until an observation, a measurement, queries the system.
Like clicking on an icon to open a file, the computer only loads it when you ask.
That's the metaphor. Superposition is just the unrendered state, computationally cheap. The collapse is the system rendering the reality, particle position, spin, whatever, only when required by an interaction or observer.
Okay, I can see the parallel. It's like lazy loading in programming.
It is very much like that. And entanglement, that spooky action.
No. How does that fit the simulation idea?
Well, if two particles are entangled, maybe they're just pointing to the same underlying data structure in the simulation's code. When you update one, the system instantly updates the other, because they're fundamentally linked at the data level, not through physical space.
Bypassing the speed of light limit because it's an information update within the system, not a signal traveling through the system space.
That's the provocative idea. It explains non-locality in a computationally understandable, albeit speculative way. Consciousness, in this view, might be the primary trigger for rendering reality.
Which leads us down a really deep rabbit hole, part 5, metaphysics. What if this isn't just efficient coding, but intentional design?
Right. If we start thinking about why reality might be structured this way, we get into some really old, really radical ideas, like Gnosticism.
Gnosticism. How does ancient mysticism connect to quantum physics?
Well, the Gnostics had this idea that our material world wasn't created by the ultimate perfect God, but by a lesser, flawed entity, the Demiurge, sometimes called Yaldabaoth.
An imperfect creator god.
Yes. And this material universe was seen as flawed, maybe even illusory, a sort of prison or a cage, designed to keep our consciousness trapped, separated from the true, higher reality, the pleroma.
Okay, so if you apply that framework to quantum mechanics,
then the weird rules aren't just how nature happens to be. They could be the deliberately imposed rules of the simulation, or the cage. Probability, uncertainty, the observer effect, non-locality. These might be the fundamental physics of the illusion.
the operating system of the matrix designed to keep us baffled.
Essentially. The laws of physics, in this view, aren't discoveries of objective truth, but decipherings of the code used to construct this reality. A syntax designed to maintain the illusion, perhaps to prevent us from seeing beyond it.
In our consciousness, the observer is central because we are the sparks of awareness embedded within this design system, maybe the very thing the system is designed to contain or test.
It's a radical flip. The quantum weirdness isn't a mystery of nature, but a feature of the design.
So this leaves us with a massive philosophical split, doesn't it?
A huge one. On one hand, standard physics. Reality is fundamentally quantum, probabilistic, emergent from chance processes governed by mathematical laws we've discovered. The weirdness is just how reality is.
On the other hand, the simulation or Gnostic Demiurge view. Reality is constructed, intentional. The mathematical laws are the elegant, perhaps computationally efficient rules of the design. The weirdness is a clue to its artificiality.
And the kicker is, the math works beautifully either way. Schrodinger's equation predicts outcomes. Bell's theorem holds. The physics itself doesn't choose an interpretation.
The calculations are solid, but the meaning, what it tells us about reality, is completely up for grabs.
That's why the double slit remains so compelling. It forces the issue. Is reality participatory? Is it probabilistic? Is it contingent on observation? The answer seems to be yes, but why is the multi-trillion-dollar question?
So recapping the mystery, the core debate still swirls around that wave function. What is it really?
It's just a calculation tool, a way to predict probabilities, like the Copenhagen view says. Just shut up and calculate.
Or does it represent something real, like the many worlds idea, where every possibility actually happens in a separate branching universe?
Or is it subjective, representing an observer's belief or knowledge about the system, like cubism suggests?
The math is agreed upon, but the reality it describes, still the biggest battleground.
It really is. And it pushes us towards thinking that maybe matter, stuff, isn't the most fundamental thing.
Which brings us to that final thought from John Archibald Wheeler.
Indeed. Wheeler proposed this incredibly provocative idea. It, from bit,
Yeah.
meaning the universe, the it, might fundamentally arise from information, from bit, that the physical world is secondary, emerging from underlying code or data.
So the ultimate question isn't, what is the universe made of?
Right.
Like atoms or strings.
But perhaps what is the universe coded with? Are these bizarre quantum rules simply the architecture of reality's operating system?
And if so, are we getting closer to reading the source code? A truly challenging thought to end on.